All right, looks like numbers have stabilized, so we will get started. Welcome everyone to our bi-monthly AI Safety, Ethics, and Society Study Group. My name is Dr. Kyle David. I'm founder of Dr. David LLC. Again, thank you very much for taking time out of your very busy schedules to join us. This is our second of 8 sessions. For those that are new or are joining us for the very first time, we're looking at Dan Hendryck's textbook, An Introduction to AI Ethics, Safety, Ethics, and Society. It's available online for free. If you've heard about this webinar series through LinkedIn, you can find the links on my LinkedIn posts. Similarly, if you go to your search engine of choice and you enter Center of AI Safety textbook and Dan Hendryck's name, it'll probably be one of the very first results that pops up for you. Today, we're going to be looking at Chapter 2, which is AI Fundamentals. And I'm going to get in to what our agenda is in just a moment. We meet the first and third Tuesday of every month. And we're going to be doing that again every month. We're going to be looking at 2 different chapters. Our final session is on April 21st. Today, I'm joined by 2 co-chairs. First is Alexandra Chebek. She is a Polish qualified advocate and intellectual property and technology lawyer focused on AI, data, and digital regulation. She advises on how new digital products, AI systems, and data-driven business models interact with European Union and international law. She is particularly interested in how regulatory frameworks such as the EU AI Act, Data Act, and GDPR shape innovation in practice. Welcome, Alexandra. Thanks so much for joining us.
Thanks for having me. I'm looking forward to the session.
Wonderful. We are also joined by John Stark. John is an accomplished governance leader specializing in the development and implementation of enterprise data and AI policies. Currently serving as the Director of Data Governance at the Indiana Management Performance Hub, he oversees enterprise-wide data and AI governance programs across the state of Indiana's executive branch. Welcome, John. Thanks so much for joining us.
Thanks for having me.
And I'm going to put the LinkedIn profile links for our co-chairs in chat. So if folks want to connect with them, you are definitely encouraged to do so. So please do that. So a little bit more about what our session today is going to look like. If you joined us for session 1, when we were defining catastrophic risk and looking at the 4 major categories of catastrophic risk, you'll remember that the session was very conversational. The co-chairs and I, we read through the chapter, we exchanged some emails, came across some major themes, and we discussed the chapter throughout our session. The content of today's chapter is a little bit different. Rather than being material that we could discuss, perhaps some ideas that are maybe open for debate, the material, the content that we're looking at today is very much more instructional. And so as the co-chairs and I were preparing for today's session, we pulled apart 2 themes or 2 types of questions. The first question, which we're going to focus a lot on, is if there's only one concept, if there was one main idea that you could pull away from this chapter, that AI governance or AI risk management folks could take away from this, what would that be? And so each of us has a concept or a main idea that we want to share with you. And the second question is, and this is something I think Hendricks does very well throughout both of the chapters that we've read as far as the study group so far, he provides lots of really good, concrete, vivid examples to give life to concepts that are very abstract. And there were a lot of those in Chapter 2. And so each of the co-chairs and I will be providing one of those vivid examples. And so taking something that is very maybe mathematic or very abstract, what's a concept that we could walk away with that we could use to help us understand a really important term such as gradient descent, or an analogy that we could present to stakeholders, senior leadership, et cetera, to help them understand something that's really very fundamental to the technology. And so that's how we've prepared today's session. It will be a bit more instructional, but hopefully, the variety amongst the three of us will make it lively and engaging for you. Similarly, please feel free throughout the session to put your questions in the Q&A section. I'll be monitoring that throughout the session and taking your questions live if they're related to the content, if we need any clarification. Otherwise, saving them for the last 15 minutes. And I think we are ready to go. So the main, as far as the most important concepts that we're going to be talking about, Alexandra is going to lead off talking about the different types of machine learning, the three major machine learning models or methodologies. John is going to talk to us about scaling laws, and then I'm going to talk to everyone about accuracy and accuracy-related metrics. All right, Alexandra, we'll hand things off over to you.
Thank you very much. Hi, everyone. Thanks, Kyle, for introducing me and arranging this session. I found the chapter very interesting because it described the basic terms in AI in very vivid and concrete examples and words, I would say. So something that struck me the most was how well it described machine learning and types of machine learning. So I decided that I would happily walk you through these three types of machine learning, beginning with a brief explanation what machine learning is within AI. So it is part of artificial intelligence, of course, and instead of following fixed pre-written rules, machine learning systems learn directly from data. And this data can be introduced to AI models in different manners, and the ways that the AI learns from the data can be categorized into three different categories: supervised learning, unsupervised learning, and reinforcement learning. So these systems, they learn from data by building models that detect patterns and relationships in data. So one important way of explaining these three different types of machine learning is by looking at how much guidance the type of model gets during the training. So this guidance is called supervision. It usually means giving the model labels and telling what the correct answer can be. So firstly, I'm going to go through supervised learning. And supervised learning is basically learning with labels. It requires the most effort from a person that teaches the model, that gives the model guidance. And basically it means that the AI model, supervised learning means that AI model is trained on labeled data. So each example comes with a correct answer, usually provided by humans. It works in the following flow, I'd say. So first, people label the data. So they have a set of data and they label it. Then the model makes predictions and compares them to the correct labels. And it adjusts itself in the course of the learning process to make fewer mistakes. After such training, it can predict outcomes for new and unseen data. So even though it was loaded, it was trained with a particular amount of data, it can come up with new data that wasn't foreseen pre-training. Examples of supervised learning can include classifying emails as spam or not spam. It can be identifying a plant or an animal from a photo. It can be recognizing a dog or cat breed or a plant breed from an image. So we train the model with a number of images of a particular breed, and then it can come up with seeing a new picture of the same breed, knowing what type of breed that is. It can identify the same breed from a new picture, and it can also, for instance, assign a song to a new genre. So that can be also an example. To give you an analogy with which I thought was a great example of what supervised learning is, it's like practicing with a book, learning something with a book that has answers in the back. So you try to solve problems yourself first. You don't have the answers given to you right away, but then you go to the back and check the correct answer, whether your thinking was all right or whether you made a mistake. Over time, the more examples you go through, the more questions you solve, the more problems you solve, you become better and better in solving further issues of the same type. However, this type of learning is limited in two ways. Limited in the sense that it's not it doesn't have limitations. So first of all, it requires human labeling or type of labeling, which can be slow, costly, and requires additional processes. So I would say this type of learning is not independent, and it's not well suited for creative and open-end tasks like writing poems, generating images. So what I would say is the most common use of AI models these days across the board. So that will be it for supervised learning. Then I would like to walk you through unsupervised learning. So this is another type of machine learning. It's learning without the labels. The model is not told what the correct answers are, basically. It's being it's being uploaded with data, it's been provided with data, but there are no labels to the data. Instead, such unsupervised model looks for patterns and structures in the data on its own. So the model searches for similarities, groups, or unusual patterns. It learns how data points relate to each other or how they are interconnected, rather than matching them to prefixed labels. Sometimes the model creates its own internal signals to guide learning. The examples of such unsupervised learning systems can be grouping customers based on similar behaviors. It can be detecting unusual activity or anomalies as compared to what is a regular behavior. Large language models predicting the next word in a sentence, so the common chats that we all know. By doing this, they learn grammar, context, and meaning without being explicitly told the grammatical rules, for instance. This knowledge, this type of models trained in this manner, can be used for tasks like summarizing text or answering questions, or using this type of models for chatbots, for instance, which are, as I said, super common. So the key point for this type of learning is that the model works itself on discovering the structure without predefined answers, and definitely requires less input from the human side, from the deployer's side. Maybe I'll use this actor for ease. However, the difficulty is that in this model is that it can often hallucinate, or it can give you wrong answers, because if the data is biased, or if the data is incorrect for some reason, or if the data is of not high quality, the model can provide outputs that are not relevant for the question. And the third type of model, the third type of learning, is reinforcement learning. So the model learns from feedback and experience. Such model learns from interacting with the environment. Such model is called an agent, popular these days, and it takes actions and receives feedbacks in the form of rewards and penalties. So it works in the following flow, in the following manner. The agent performs an action. The environment responds, whether it's correct or not, whether it's appreciated or not. Then the agent receives a reward or a penalty. And over time, it learns with actions that lead to better results. So it learns which responses were appreciated, which were rewarded, while the others were penalized, basically. There is no need for a pre-labeled dataset in such a training model because the agent learns from experience, as we call it, and gradually improves its behavior. An example of reinforced learning models are robots learning to move or navigate in an unknown space, systems learning to play games like chess or Go, and systems that optimize decisions that happen step by step, such as traffic control. The key characteristics of such systems are they're focused on decision making over time, they learn through trial and error, and they're useful in dynamic and changing environments. So the environments that are not predefined, there is no right or wrong, I'd say, in these types of environment because they can dynamically evolve. However, the biggest drawback of such systems is basically that, especially in the initial stages, they are not very useful because they don't have this what we call experience yet. So it requires a significant amount of development and trials and errors to develop a system that is relevant and actually useful, and that can a system that can be relied upon to an extent. So this is the biggest drawback of this type of system. That'll be it for the three types of learning in ML.
That's great. Thanks so much, Alexandra. And I think each of the examples that you provided there for, I really like Hendrik's example of using a textbook to learn, right? You have like a practice quiz as you're going through the chapters, and then you can flip to the back of the textbook to see if you got the answers correct. I think that's really helpful. And on the topic of reinforcement learning, my maybe one of my favorite documentaries ever is AlphaGo. And
Mm.
for those in the audience that haven't watched AlphaGo, it's available for free on YouTube. And it's about Google DeepMind's creation of a system that could play the game Go. And if you're unfamiliar with Go, it's a bit more strategic than chess, from what I understand. It's very popular in East Asia. And so AlphaGo is fantastic. And also, Alexandra will talk about AlphaFold later. They did like a sequel to AlphaGo called it's called The Thinking Game. I think it's called The Thinking Game. It's also about Google DeepMind, and it's about their creation of AlphaFold. So I don't want to give any more spoilers away, but that's also available on YouTube. So that's fantastic. Thanks very much, Alexandra. All right, John, over to you for scaling laws.
Yeah, thank you. Thanks for having me today. Really excited to talk about this because I think a lot of people outside of this group and the people that are in this industry think a lot of this is just magic. Um, and when we're able to kind of demystifies that and show that it's science and math and technology, pretty basic things, I think it becomes much more real and tangible for people. So I really wanted to talk about scaling laws today. And I think, it's no accident that AI is getting better. It's following a predictable growth spurt that we can actually measure. And so, with this predictable project or progress, we used to think that, AI was hit or miss, but scaling laws show that, a model's error rate, the loss, drops predictably as we increase three things being, the parameters of the math it can handle, the info it learns being the data, and then the brain power used to train it, so the compute. Being able to essentially put this into an equation makes things much more tangible, and putting it into the governance realm here in the U.S., it's kind of a patchwork of rules and laws and regulations and things like that. So here in Indiana, we really rely on the NIST AI RMF, which something so concrete as scaling laws really helps us for the measure function of the NIST AI RMF. And that really allows us to kind of help predict how the model will perform before it's even built. And then we can plan for risks rather than reacting to them after deployment. One of the scaling laws that I kind of want to touch on is the chinchilla rule. So this research shows that there's a sweet spot ratio between, data and the model size. And if you get this wrong, you're kind of wasting resources. But if you get it right, you achieve that kind of optimal compute. And with that, the chinchilla scaling law emphasizes again that compute, making sure that you're defining and narrowly identifying the precise balance between the required number of parameters in the model and the amount of training data it consumes, focusing specifically on, emphasizing on data over size. So specifically highlighting that, AI systems are undertrained on data, and that the law demonstrates that that smaller models with fewer parameters can actually sometimes outperform larger models, if they're trained, on more fit for purpose data that's significantly more trained on significantly more data. With this, the example, the chinchilla model, I kind of touched on it briefly, but putting a finer point on it, it was a large language model that only had, which is hilarious to say, only 70 billion parameters. But in this day and age, that's, quite small, it seems like. But the chinchilla model outperformed much larger models because it was trained on vastly larger data sets. And with this, and circling back, this is one of the things I loved about this chapter, because being able to put your hands on concrete things, and kind of the liberal arts degree person in me kind of hates that I've come here, but putting it back into math and concrete science, so those scaling laws, including the chinchilla, really allow researchers to quantify, predict a model's performance based on those two primary variables, meaning the size, the model size, and the data set size. Being able to quantify these things, I can't stress enough. It seems like there's a lot of mysticism out there in marketing hype about it's magic. And it's like, we can actually show the work on this. We can pull the curtain back and point to, the equation. And I won't, read the equation out of the chinchilla scaling law, but I think that's critical in this day and age where there's so much marketing just being screamed out into the ether, it seems like. And so that's why I really loved that the scaling laws were focused on in this chapter.
That's great, John. Thanks. Yeah. And if you're not familiar with Dwarkesh Patel, he has a podcast, and he's also written a book. It was a series of interviews called The Scaling Era. And he talks, about the scaling law, and the period that he's termed as the scaling era is 2019 to 2025. So a history of the present, so to speak. And when you understand how scaling laws work, how they're structuring the data center infrastructure build out around the world, you start to see what they're trying to do, right? More compute, more data, better models and performance. And this is an active debate. Some, researchers that are, very well known feel that we may have hit the edge, or we may have very come as close to possible as we can with the scaling era, and that what we actually need is different algorithms or different system architectures and so forth. But the scaling laws are certainly very important for getting us to where we are today. So great, John, that was fantastic. I appreciate that. Okay, so for metrics, I am going to give folks a little bit of a sneak peek into the updated version of my AI Governance Professional certification course, so the AIGP. Can I get a thumbs up from my co-chairs? Can you see my screen here okay? Wonderful. Okay. So I want to talk about accuracy. I want to talk about how accuracy can be very misleading. And again, I think Hendrix does a great job discussing this in the textbook. And for AI governance professionals, for folks that are working with internal teams to build a model, or who are working with procurement and acquisition teams to perform due diligence on vendors from whom you may be procuring a model, accuracy is a really important concept. I feel that for folks that don't understand accuracy and how it can be misleading, it's going to be very easy to be duped by folks that are great at marketing. Saying, for example, that our model is 99% accurate. That sounds great, but if you don't know the right questions to ask, the follow-up questions, then that 99% figure could be absolutely useless. And it could actually demonstrate that this model is more than flawed, that it is absolutely useless. And so we're going to look at some concrete examples of that. Before we define accuracy, however, it's important that we understand what a confusion matrix is. And it's a confusion matrix because it's a bit confusing. That's my joke. So I'm going to show you what the confusion matrix is, and then I'm going to define true positive, false negative, true negative, and then we're going to walk through an example of this. This is a confusion matrix. We see on the left-hand side, we have what is predicted by our model. This is used for classification models, for example. The example that we're going to look at is trying to identify fraudulent credit card transactions and how successful a model may be. So on the left-hand side, we have that the model has predicted this is a positive case, this is fraud, or the model has predicted negative, this is not fraud. And then in the top, we have the actual result, okay? So positive being, yes, this was fraud, negative being, no, this was not fraud. And if that's a little confusing, then hopefully this next slide will make it a little easier for you. So for true positive, what the matrix does is it says, again, this was predicted positive. It was actually positive. So the model has said, yes, this is fraud. And when Alexandra earlier was talking about the textbook for supervised learning, I want to check my answer in the back of the book. So I've gone through the activity. I'm the model here. I'm saying, yeah, this is definitely fraud. I checked my answer at the back of the book. Yes, this is fraud. Great. I got the answer right. True negative is I'm saying, nope, this is not fraud. This is negative. I'm going to check my answer in the back of the book. Right. Okay, good. That's negative. I'm right again. And so true here is saying that my prediction of positive was true. My prediction of negative was true. These are true predictions. For false positive and false negative, it's the opposite. So I'm looking at an example in my textbook. I'm saying, yes, this is an example of fraud. I check my answer in the back and I'm wrong. It was actually negative. This is what you might call a false alarm. So I've said, oh, look, fraud, we've got fraud here. We're going to shut someone's credit card down. And then that person's going to call and they're angry because they're like, hey, I'm on vacation in Puerto Rico. You shut my credit card down. What's going on? Oh, so sorry. We predicted that as fraud, but it's actually not. And then false negative, this would be a miss. So I'm looking at my case, I'm saying, oh, yeah, negative, this is not fraud, but it turns out to actually be fraud, right? I'm checking my answer and it actually is fraud. So this is a miss. I was wrong, and now some identity thief has a new jet ski, right? That John unfortunately has paid for, all right? So what does this actually mean in terms of accuracy? First, what is accuracy? Accuracy is a measure of the overall performance of a classification model. Again, in our case here, we're classifying fraud in credit cards. We could also be, perhaps this is a medical imaging system that is looking at x-rays or MRIs and is trying to identify tumors or cancer. This could also be, I believe Alexandra was using the example of plants or different species of animals, right? That would also be a classifier. And a model's accuracy, this is one of our primary indicators of model performance. It can tell us the correctness of a system's outputs, how effective that system is, as well as task completion success. And knowing how accurate a system is really important for evaluating that model, for determining system reliability, as well as for doing quality assessment. But, and this is one of the main takeaways with accuracy, and again, Hendricks does a good job, communicating this in the book, accuracy can be very misleading. And so going back to our example of fraud detection, let's say that I have 1,000 cases, financial transactions, and 1% of those transactions are fraudulent. If the model predicts not fraudulent 100% of the time, then it is 99% accurate and 100% useless because it has missed 100% of the fraudulent cases. So again, looking at our example, we've got 1,000 total cases. Of those, 1% are fraudulent. That's 10 transactions. There are 990 legitimate transactions, but it hasn't caught any of the fraud. And so these are what our numbers would look like on the actual confusion matrix with regards to our true positives, true negatives, and false positives. And I'm going to pause right there. We're going to go a little deeper into this example, but I'm going to shoot it back over to Alexandra and John. We're going to shift now into some of these concrete examples that we found in the textbook that we felt provide life, right, for some of these more abstract concepts. So Alexandra, we'll go over to you. I think you're going to talk about AlphaFold and narrow AI, right? You're muted.
Of course. What is it? 6 years into COVID reality and still being muted on the call. Sorry for that. So yeah, I found the AlphaFold example an interesting one because so Hendrix provides it to exemplify how narrow AI, even though it's an AI system that is designed to perform a single specific task. So it is not supposed to think across numerous topics, concepts, and themes. It's just designed to perform a single task. It's a type of AI, it's narrow AI, so also called weak AI, and it's to be very graphic about it. It's supposed, of course, to overreach what a human being could potentially reach, but it's not as intelligent as a human being because it only performs one task, so it does not have this ability to think in an abstract manner, I'd say. So why AlphaFold example is an interesting one is because it exemplifies how even narrow AI operates in a manner that is still not understandable to human beings and works within what's called a black box way of problem solving, which is irreversible. It cannot be reverse engineered to understand how the AI came up with the solution while still being considered narrow AI. So because it's only designed to perform in this one narrow topic for which it was designed. Better than a human being, but only within the constraints of one specific task. So the AlphaFold example as such, it's about discovering how proteins fold into 3D structures, and by predicting how they're going to fold into these 3D structures, predicting what they can be, what will they develop into. So basically, biology for over 50 years since the development, since discovering the issues related to proteins and their development and folding, biologists faced a hurdle, which they knew that proteins are made of long chains of amino acids, but those chains fold into incredibly complex 3D shapes, which I referred to before. So this 3D shape of protein chain determines its function. So if you don't know the shape, you don't know how it works or how to stop it. So for instance, if the protein is developed into diseases, then you wouldn't, without understanding the shape into which these millions of proteins fold, you wouldn't know towards which direction such disease would develop and how to stop it basically from further folding and further growing basically. So the AlphaFold tool was designed to for a specific purpose, predict the protein structures rather than so it was designed to predict the protein structures, so the chains. However, the whole black box issue around the AlphaFold that cannot be really discovered how it operated within this task was that it discovered it didn't just follow the human instructions to predict protein structures, but it developed its own internal logic to solve the folding problem. So to discover, to predict into what shapes will the protein chains fold consequentially. So it acted in an unpredicted way, and it found shortcuts and patterns in biological data that human experts couldn't spot for numerous years. And effectively, it taught scientists how to predict the ways these protein chains will fold, and further how to stop them from further development, and how to stop what the proteins can be used for in case of, for instance, the diseases. So basically the bottom line is that even though the AlphaFold was intended only to predict the structures, it also discovered something that was one step further, so how the proteins fold and what can be, and data that can be derived from this folding structures. And further, the scientists were able to discover how to stop what is developing from this from these structures. So again, AlphaFold couldn't be used for any other task than predicting the protein structures. So it couldn't generate an image, or it probably couldn't even say anything else within the issue of proteins. But within this single specific task, it went as deep as the numerous scientists couldn't go. And also there is data available that it would take like about a century for a human being to go through all potential calculations around that. So, and while the AlphaFold did it within minutes or a similar amount of time. So that was the example that I found extremely interesting to illustrate how narrow AI, even though designed for a specific task, still operates outside of human instructions. So it's not a simple algorithm or not a simple software that does not have this item of abstract thinking. But this is this is the example of how narrow AI is still an abstract concept in the way it solves issues.
That's great. Thank you, Alexandra. One thing that I felt really useful, and again, something that you can take to stakeholders and leadership as you're briefing them, Hendrix talks about imagining AI with regards to capability. And he's talking about, narrow AI, AGI, artificial superintelligence. He has two other levels that are between AGI and artificial superintelligence. I won't get into them. They're on page 59. But what I think is useful is thinking about or trying to map or place an AI model or system based on two axes. So one axis would be an intelligence axis, and then the other one would be, skill or the ability to generalize. And so AlphaFold 3 is going to be very far on intelligence, right? It can beat every other human being at predicting protein folding, okay? So it's going to be, very far on intelligence, but on the axis of generalization, it's going to be very low because that's all it can do, right? It can do this one thing better than other humans, but it cannot take that same that same skill set and apply it to other domains, even within biology. Same thing with AlphaGo. It's going to beat all humans at Go, or at least the current iteration of it is. But it would not be able to beat people at tic-tac-toe, for example. So I think that's a really important concept, and thinking about, placing AI based on capability is very useful. Thank you. Also, just one other data point. I think biology PhDs would spend 7 years mapping one protein. And AlphaFold 3, or maybe it was 2 or 1, was able to do them all overnight once it figured it out. So great. Okay. Yeah.
Sorry, I think I came across 5 years even,
Oh,
so
okay.
even longer.
Close. Yeah. Great. All right, John, over to you.
Yeah, great. Circling back to the thought of kind of taking away the magic, of AI, so that we can explain it to our non-technical stakeholders. One of the examples I found really interesting and helpful in the book that Hendrix had was the story, or this example of the blindfolded hiker. So thinking about a hiker, they find themselves, like completely lost. They're lost on the top of, a mountain range, on the peak, dense, complete fog, and they need to get down to safety, down to the valley, but they can't see, further than 2 inches in front of their face. So this hiker represents, our AI model during the training phase, and the mountain that they're standing on, it's obviously not made of rock. It's, the mathematical loss function, and every point that mountain represents a mistake that the AI could make. So every point in the mountain range, up and down, is a potential for a mistake there. So the higher up they are, the bigger the error. The valley at the bottom is obviously our target, unless you're really just wanting to live at altitude and elevation. The point of minimum error, where the AI provides the most accurate results, is going to be the valley, which is our target. So since the hiker is blindfolded, they can't just point to a valley and walk there. Instead, they got to use their feet to kind of feel the slope, feel it out of the ground immediately around them. They can't really find the direction that goes downhill the steepest, in any technical terms. They have to find the direction that's the most efficient, calculating the gradient. So they take a single step in that direction. With this, and kind of in the governance sphere, that step is powered by, and this always trips me up. I love giving presentations with words that I know that I'm going to mispronounce. So backpropagation. But the model feels the error at the top, basically the error, and sends a signal back to its layers and adjusts its internal weights and biases to get a little bit closer to the floor. So where this kind of comes into a little bit more practicality, thinking, if the hiker takes a massive leap, they might jump over the valley and end up on another peak. If they take a tiny shuffling safe steps, they'll never reach safety before sundown. And with that, circling back to one of the practices that we utilize here the most, the framework, or one of the frameworks, the NIST AI RMF, it really focuses on and reminds us that valid and reliable is the base of all trustworthiness. So if the data we provide to that mountain is biased or poor quality, the mountain itself is a lie. Our hiker could feel that they've reached the bottom, but they're actually walked into a local minimum, like a ditch that looks like a valley, but it's actually a failure in a real world setting and not a valley. So when we're thinking about these things, I think it's important to make sure you're kind of auditing the terrain, to ensure that it's built on authoritative sources, and that the hiker, the person building the model or training the model, has the right accountability structures in place, so that if they lose their way, there are ways of correcting that.
Yeah, that's great, John. Thank you. And for another thing I really like about Hendrik's book is that, he will go on for, 10, 15 pages explaining. I mean, it's technical. This is a pretty technical chapter, but I feel that along with the technical explanation, the, equations that John was talking about, um, there's also, a plain language, or at least for these concepts, as plain language as you can get. And at the end of every section, every 10 or 15 pages where he's explaining something very technical, there's, a really good plain language, straightforward explanation of how this process happens. And so John was talking about the gradient descent. How do we minimize loss in a model so we can get it to be as accurate or as correct as possible? And on page 96, there's a breakdown essentially of 7 stages of how this learning takes place. And I'm not going to go through that here, but again, I think it's really good. It's maybe about 2/3 of the page. It's, if you've been reading along and you were a little lost, as long as you've picked up the major terms, right? Like back propagation, forward propagation, loss calculation, which is all defined in this chapter, then that summary can be very useful. So thanks, John. That's great. Sorry, I muted myself, just a habit. Didn't mean to do that. Okay, so I'm gonna go back to our example of trying to detect fraud and accuracy, and how accuracy alone can be misleading. And so just as a little bit of a review, we're looking at this real life example of a model that's trying to detect fraud. We have 1,000 samples. Only 1% or 10 of those transactions are actually fraudulent. So there are 990 legitimate transactions. And a model that said everything is legitimate is 99% accurate, but 100% useless because it has failed to detect any of the fraud. This is what those numbers look like on our confusion matrix. And so this is how accuracy is calculated. So we have our number of total correct predictions, which is 990, total number of predictions, which is 1,000. We do our math, we get 99%. So that looks good. If a marketer, if a vendor comes to your organization and says, hey, we've got this model that's 99% accurate, that sounds good, but you have to dig deeper. You have to dig deeper. And the 3 metrics that you want to look at or you want to ask for are precision, recall, and the F1 score. The importance or the weight of these different metrics is going to depend on your use case. And I have 3 use cases that we're going to look at over the next couple of minutes here. So precision is measuring the correctness of the model's positive predictions. Recall is measuring the model's breadth. And the F1 score is the mean of precision and recall. And we have examples for each of these. So precision is asking the question of all instances that the model predicted positive, how many of those were actually positive? And so precision is all of our true positives divided by the sum of true positives and false positives. In our case, it was 0 for all of these. So our precision is undefined or 0%. So a model that's 99% accurate with 0% precision is a model that you don't want to invest in. Similarly, with recall, of all actual positive instances that exist, how many did the model find? And again, we have our true positives divided by the sum of true positives and false negatives. In our case, we have 0 divided by 10. That's still 0%. So it's 0% recall for this model. Again, that's no good. And then finally, our F1 score. This is a mean of precision and recall. And you can see the numbers added up here, right? We have 2 times 0, which of course is 0. So for all 3 of these sub-accuracy metrics, for precision, recall, and F1, the model has failed. So again, that top line number of 99% accuracy, you have to dig deeper. And really what's important here is context, because a high false negative may not be bad depending on one context, but it may be bad in another. And so the two additional examples I want to look at here, and these come from also come from Hendrix's textbook, is cancer detection and a water sensor in an autonomous vehicle. And so for cancer detection, missing a cancer diagnosis, so a false negative, can be more dangerous than a false positive. And let's just imagine that you or a loved one go to the doctor and they're going for, let's say, an annual or whatever, a screening that they're supposed to do frequently due to age or medical history. And the doctors, the tests come back and say, hey, we think that, we've located a tumor and it may be cancerous. So that, that person is going to have to undergo further testing. Maybe they have to do a biopsy. They're going to get some blood work done. Let's say all that comes through, and thankfully the tumor is benign. It is not cancerous. There's no problem there. We would rather have that happen than for the cancer, for that tumor to not be detected at all, or for it to say that, hey, this is actually is not cancerous, and then to not be diagnosed, to not be treated, only later for the individual to develop symptoms or for that to metastasize and, to cause, for that person to be very unwell, unhealthy, have to go through chemo or, of course, may pass. So in this case, a false negative for cancer detection, a higher false negative rate might not be a bad thing, right? A false negative with regards to an autonomous vehicle, however, could be fatal. And so imagine that your autonomous vehicle has a water sensor. The water sensor predicts that the road is wet. So we have a false positive. Well, that model, that car is going to drive a little more carefully because it's predicting that the environment is wet, that it could be raining or it recently rained. Look at the other case where it says, all right, well, I'm sensing that the road is dry, that it is not wet, and therefore it does not adjust its performance, and it skids on a puddle of rain and crashes and leads to a fatal accident. So context is also really important. Again, I think the summary here is understanding the submetrics that we need to request when we're doing due diligence or we're working with subject matter experts, and understanding the context as well, right? What is our false negatives? What does that look like for this specific situation? One other thing, and this is what I'll close on, trade-offs are really important as well. We may not be able to optimize everything. And so think about accuracy versus latency. You can have a model that is very accurate. It takes more time to perform its computations, to check its work, but that extra computation is going to require more time, which means that the customer, the user of the system, has to wait longer to get their output. For accuracy and interpretability and explainability, our most transparent, interpretable, explainable models are going to be, decision trees, for example, or linear regression models. Those, however, are often not as accurate as a deep learning neural network. And then finally, when it comes to accuracy, there's a trade-off with privacy and fairness. If we have more sensitive data about someone, if we collect more data, if we're not implementing any type of de-identification or differential privacy, then we may have, as accurate data as we can, but of course that creates potential problems for privacy and for fairness. So these are some other important trade-offs. Again, Hendrix goes over, and I think, again, with regards to due diligence, reviewing models, working with subject matter experts, it's important to ask these types of questions. All right. So I've been monitoring Q&A and didn't see a whole lot of questions, which is why I just went through the full example there. But we do have about 5 or 6 minutes for any follow-up there. Or, John and Alexandra, for either of you, any comments? Yeah, John, go ahead.
Yeah, so related to the chapter, it kind of went through the AI winters and the coming back out of them and so on. And the thing that everyone is saying is that we're in an AI bubble, or potentially it's going to pop soon. And so the thing that I'm curious about and would love to get your thoughts on, and Alexandra as well, is if we are in an AI bubble and that bubble does pop, do we go into an AI winter, or are we somewhere in between, the hype of where we're at and a winter?
Alexandra, do you want to go first?
Yeah, maybe quickly. So I think we already are to an extent from the EU perspective. I'm gonna speak from the EU perspective. So where we are at the moment, what I identify is that we are past the super hype and past believing we're on the border of reaching super intelligence and it's gonna be tomorrow if it's not today yet. And I think this type of, and also the idea that this AI is this some sort of extreme power that is going to take over the world and support us or destroy us. I think we're past that point, to exaggerate a little. Where we are now, I think, is we are trying to uh, live with the state of the matter, deploy it in our, like, they use it daily to an extent it is possible, deploy it in commerce, deploy it in our daily operations in business, etc., while also, which is obviously very important for my domain, while also being within the constraints of the newly introduced regulations. So I think where we are now, I wouldn't call it a winter, I would call it everyday life, or the mundanity. If it's mundane, is there an adjective for that? So the mundane reality of living with it, basically. It's like with data protection, almost 10 years ago, GDPR was introduced, and there was so much hype around personal data, and it's going to kill the business, blah, blah, blah. The US companies are not going to come to Europe, etc. And where we are now, we're just living with it, and it didn't stop innovation, etc. I'm bringing up the GDPR example because the data issue is so parallel to talking about AI and regulations around it. So I think it's not winter, it's reality, I'd say, maybe.
Yeah, I think that's really good, Alexandra. One individual I think everyone should follow if you don't already is Ethan Mollick. He's a professor at Wharton School of Business, and he regularly posts on LinkedIn. He's got a Substack, and he's following all of the debates. And one thing that well, I mean, really two things I think that are important is that the the systems that we're using today are the worst systems we're ever going to use. They are only going to get better. And that has held true since ChatGPT 3.5 was released in November of 2022. So I think that's one important consideration, is that even if development towards AGI or artificial superintelligence, if we never reach that, or if we don't reach that for another 20 years, the current technology is going to continue to be refined. The other major consideration is adoption. We're still adopting the very basics here, right? How do we build out agents? How do we automate? How do we get the full use out of the large language models that are available? Not only how do we get them into our organizations, but how do we train folks up to use these tools? And that's something that is still lagging as well. So I feel that the research, which is getting billions of dollars in investment, alongside the data centers and all of the companies, the research is still taking there, and it's going to take time for that to come out. So I agree with Alexandra that even if innovation stopped, right? Like if we're hitting a point where there's going to be no innovation for a while, what we already have needs to be implemented, refined, made more efficient. And I think we'll continue to see gains in the economy and across many different sectors due to that catch up.
Yeah, I think and I know we're tight on time. I think we're at that point though where it can actually be implemented in a meaningful way at, not to sound cheesy, but at scale where we may not have been in the past. So I agree with both of your assessments of it.
Wonderful. Thanks very much. Okay, we are at time. Just one quick note. I'm still looking for one more co-chair for our next session, which is on February 3rd. The chapter is on, I've got it right here, single agent safety. So this is textbook chapter 3. If you're out there, if you're interested in this topic, shoot me an email, drdavid@drdavidprivacy.com. In closing, John Stark and Alexandra Chebek, thank you so much for your time. I really appreciate it. And to the audience, thanks for coming by. Looking forward to seeing everyone in a couple of weeks for our next session. Take care.
Thanks.